The traveling salesman problem is a classic problem in computer science. The problem is an abstraction of a real-world situation. A salesman wishes to visit 25 cities over the course of a few months. He wants to calculate the quickest route between the cities so he doesn't have to waste any time traveling. His first idea is to just draw out every route and calculate which one is the shortest. However, he quickly realizes that there are far too many possible routes. He calls his friend, a computer programmer. She writes a script to run through the possible routes and find the fastest one. She lets the computer run for hours, but there is still no answer. The salesman and his friend have come across one of the most infamous problems in computer science. Given a set of points, there is no known fast algorithm for calculating the shortest route between them. Over time, programmers have developed shortcut algorithms that eliminate the need to run through every possible route, but solutions for large numbers of points still take an impossibly long time. The traveling salesman problem has a wide variety of applications. The most obvious example is in delivery processes. Services like Amazon or FedEx need to assign routes to their delivery drivers, and a solution to the traveling salesman problem would help them pick the optimal routes. A less obvious example is in the manufacturing of electronics. Manufacturers often face a problem where a number of modules need to be connected by wires in any order. They wish to choose the order that requires the least amount of wire, which makes it a traveling salesman problem. While finding the shortest route has proven very difficult, computer scientists have developed approximation algorithms that produce a reasonably short route in a reasonable amount of time. This way our salesman can spend less time figuring out the best route and more time traveling a good route. One approximation algorithm uses mathematical tools like space-filling curves and fractals to approximate a solution. Fractals are never-ending patterns that are created by repeating a process over and over again in an infinite loop. A famous example of a fractal is shown here, the Mandelbrot set. This is created by plotting the set of complex numbers for which a sequence is bounded. Nature is full of fractals, such as trees, rivers, coastlines, mountains, and this picture here of a fern, which you can see is self-similar. Note how the leaves have repeating patterns as you look closer and closer. A curve is any continuous function defined on the interval from 0 to 1. We can think of continuous as meaning that there are no holes in the line, so it's essentially one long string getting stretched. A space-filling curve is a curve whose range fills the entire unit cube. This could be a two-dimensional unit square, or it could be a unit cube in 3 dimensions, like shown here. You can see that there's one long line filling up the entire cube, and while there are spaces between the line now, you can imagine the line getting denser and denser until it fills the entire cube. One example of a space-filling curve is the Hilbert curve. These are space-filling curves that also satisfy the properties of fractals. The curves are built recursively in orders, as you can see 6 of them here. Each order makes the curve increasingly complex, and as the order approaches infinity, the curve becomes a fractal. So as you look closer at the curve, you see smaller versions of itself. Another example of a space-filling curve that's very similar to the Hilbert curve is the Sierpinski curve shown here. It has all the same properties as the Hilbert curve, like being a fractal, but it uses a different pattern. Space-filling fractals, like the Hilbert and Sierpinski curves, are often used to approximate designs when relative distance needs to be preserved. An example of a use of a Hilbert curve is in the field of image processing. You can see here that a Hilbert curve is being used to create an image of a cat, where some parts of the curve are denser to create a darker image, while the sparser parts of the curve create a lighter image. We can simplify the traveling salesman problem by thinking about the one-dimensional version. In this case, we would just have one row of cities to visit. We start at the leftmost city and begin traveling to the right until we hit the rightmost city. Then we turn back around until we return to the leftmost city. This is always the best route. Why? If we skip a city, we'll eventually have to go back and hit it again, making the trip less efficient. Things become more challenging in 2 dimensions. While defining a leftmost city is not difficult, what would it mean to go to the nearest city on the right? In 1 dimension, we have a single direction we can travel in, but these points are in 2D, so we want some kind of transformation that will take us back and forth from 1D to 2D. Once we have the points in 2D, we can just transform them in a way that we can view them in 1D, and then we can use the algorithm we talked about before for the 1D case. The space-filling fractals we discussed before have properties that make them suitable for this task. A key observation about the Sierpinski curve is that it preserves locality fairly well. That is, points that are close together on the curve are also close together in 2D space. The reverse is true as well. Points that are close together in 2D space will be close together on a sufficiently fine Sierpinski curve. This is not perfect, but it serves as a useful approximation. The trick is then to create some curve based on the Sierpinski pattern with some desired level of detail. We approximate each city's position by the closest point on the curve to the city. We then simply follow the curve and list the cities in the order we encounter them. This approximates the ideal path for the salesman.